Okay.
Okay, so can you see the slides?
Yes.
Yes, we can.
Very visible.
Yes.
Okay. Okay, so let's start. So it gives me great pleasure to introduce the speaker of today's IPC talk, Professor Eugene Demler from ETH Zurich. Professor Demler completed his PhD at Stanford University with Professor Xuesheng Zhang. He then moved to Harvard University for his postdoctoral work as a junior Harvard fellow. Soon after, he joined as faculty to the condensed matter theory group at Harvard University. And finally, recently in 2021, he moved to ETH Zurich, where he's now a professor of theoretical condensed matter physics. Professor Demler has received many distinctions. I would only be able to name a few. The Sloan Fellowship in 2002. He was elected as a distinguished scholar at the Max Planck Institute of Quantum Optics in 2015, the Simons Investigator Award in 2021, and the Hamburg Prize for Theoretical Physics in 2021. Professor Demler's research is within the broad scope of condensed matter physics. He has made numerous key contributions to our theoretical understanding of strongly correlated quantum matter, ranging from the physics of unconventional superconductors, quantum magnetism, topological phases, and maybe most famously known for quantum simulators in cold atomic platforms. Professor Demler has particularly strong scientific ties with the Israeli research community, and we are very excited to have him here today. So you are encouraged to ask questions via the chat during the talk. I will try to collect a few of them, and we might have a short Yes.
Let me just say there are, by accident, there was a different link sent. So if we can give 2 more minutes for people from the other link to join this one.
Okay, I will, okay, we can start in a few minutes, that's fine. And okay, going back to question instructions. So you are encouraged to ask questions via chat, and of course we'll have the usual question time at the very end of the talk. So let's wait a few more minutes for other people to join, and we'll start, let's say, at 4:10. Okay?
Sounds good.
So Serge, did you send a new link to, let's say, the Weizmann people or something? What's the... Okay. Okay, so let's not delay this further. So without further ado, let's start the talk. Thank you very much, Eugene, for agreeing to be with us here today.
Well, thank you, Snir, for the invitation and for this very kind introduction. I'm honored and delighted to see so many friends. And it's really a great privilege to tell you guys about the work we were doing lately. A lot of it is work in progress, so I will appreciate feedback, comments, criticism. And let me start by acknowledging my collaborators. The main credit for theoretical work should really go to my standing theoretical colleagues, Fabian Grust, who was a postdoc at Harvard and is now a faculty member in LMU, Annabelle Bort, who first came as a visiting student to Harvard and is now postdoctoral fellow at ITAMP, Dries Sals, again, who was the postdoc at Harvard and now has his own group at NYU, and Kushal Sitharam, who is a graduate student actually applying for jobs this year. And what was also particularly exciting about the work is an opportunity to collaborate with our experimental colleagues, especially with the group of Emanuel Bloch from Munich, the group of Markus Greiner from Harvard, and these were cold atoms experiments, and also on ion-based quantum simulators. We had a great collaboration with Chris Monroe and Marcus Itina's group at the University of Maryland. Okay, so in a way of introduction, let me remind you that what makes many of us excited in physics is the idea of universality of physical laws. In fact, one of the most kind of interesting manifestations of this was a popular article written by Steven Weinberg when he was asked to explain the Higgs particle soon after its discovery to readers of the New York Times. And the way he started his article was by saying, well, let us think about what's happening in a magnet, again, emphasizing that concepts like broken symmetry, collective excitations are common to a variety of systems. And to me, an even more striking manifestation of this universality was actually fortuitous coincidence in time between the discovery of the Higgs excitation at LHC. So here you can see this famous plot of the proton-proton collision, and this peak is the Higgs particle. And in order to observe this Higgs excitation, experiments had to be done at energies which are 12 orders of magnitude higher than room temperature. In about within a time difference of 1 week, our colleagues at the Max Planck Institute published a paper on experimental measurements of the Higgs excitation in the superfluid state of atoms in optical lattices. And in this case, experiments had to be done at energies and temperature scales which were 12 orders of magnitude smaller than room temperature. So we can talk about microscopic models which are separated by 24 orders of magnitude, yet they share fundamental physical principles. And in fact, this is no longer just subject of fascination, but in some sense it became a tool for physicists. And this was particularly well illustrated by Richard Feynman, who suggested the idea of quantum simulators, that we can use quantum systems to understand more challenging quantum systems. And a lot of my talk today will deal with a very specific type of quantum simulator, and these optical lattices, which is sort of periodic potentials created with standing waves of light, and then fermions loaded into this periodic potential. This gives rise to a microscopic model, which is very similar to the microscopic models that describes electrons in strongly correlated electron systems, specifically in high TC cuprates. Again, we see that the energy scales differ tremendously. However, the idea is that we have very similar physical model, and that because we have been struggling for so long to try and understand physics of high TC cuprates, like by doing brute force theoretical analysis, we can hopefully get some insight into this fundamental model by analyzing experiments on ultra-cold atoms. And let me also emphasize one interesting aspect of current experiments, and this is using quantum gas microscopes. So these systems allow to measure every particle in a many-body state. So a result of an experiment looks like, as this picture, you see, it's really like a collection of points which basically tell us where every atom has been detected. So in some sense, we can compare this way of doing physical experiments to pointillism, right, which was a style of painting among Impressionists, where, say, in this painting by Seurat, this picture has not been done with traditional brush strokes, but with individual dots. So what we will be discussing today is we will look at this kind of pointillist picture provided by nature, and we will discuss what kind of physics we can learn by looking at these images. And one of the ideas which has been becoming popular lately is that since output of scientific experiments is now more like images, then we should use tools of machine learning. So only have a brief discussion of this, but I think it is an exciting future direction. So this is an outline of my talk. I'll start by reviewing sort of a simple model of magnetic polarons and how we got new insight into magnetic polarons using recent experiments with ultra-cold atoms. I'll point out interesting connections to quantum chromodynamics. Then I'll talk about how we're also understanding the transition between this kind of regime where we have magnetic polarons which weakly interact with each other to a more conventional regime of Fermi liquid as doping is changed. Again, we understand it based on what we have seen in the experimental data rather than kind of theoretical calculations. I'll also talk about like using convolutional neural networks to compare different theories to experiments. And then finally, if time permits, I want to bring up a question of using quantum simulators to address problems beyond, which are interesting to people beyond the physics community, in particular to people doing biomedical research. And I'll talk about some of the work we have been doing in terms of using quantum simulators to solve the problem of NMR inference. Okay, so let me start by talking about magnetic polarons in 2D systems. Since the audience is broad, I want to point out this, just bring up one fundamental phenomenon in kind of lattice models in the physics of electron systems such as cuprates or quantum antiferromagnets, and this is super exchange interaction. So think about a lattice model where we have localized, almost localized orbitals, and fermions can tunnel between these two orbitals. There's strong repulsion for two fermions on the same site. And then we can ask, well, what, obviously, in this case, we prefer to have one fermion per site, but will they be will the spins of these two fermions point the same way or in the opposite direction? And you can immediately see that if spins are pointing the same way, then kinetic energy is fully suppressed because now tunneling is not allowed by the Pauli principle. Whereas when spins are anti-parallel, we can sort of at least have virtually, system can virtually go into a double occupied state and therefore lower kinetic energy somewhat. So if one does this calculation, one finds indeed that this model can be written as a sort of spin exchange Hamiltonian, where J is this super exchange is just given by the usual second order perturbation theory. So matrix element, which in this case is tunneling square, divided by the energy denominator. So in terms of microscopic model, what I will be showing you is we will talk about fermions in an optical lattice, and they are described by the Fermi-Hubbard model. It has hopping and strong on-site repulsion. Sometimes I'll use a model which is believed to be a very close sort of descendant of this model. This is the so-called TJ model, when we say, okay, double occupied sites, very high energy states, we can integrate them out, and then what we're left with is a single particle hopping, but with a projection that no double occupancies are allowed. And there is antiferromagnetic superexchange interaction. Okay, so now let's start with something simple. We start with a configuration that has one fermion per side, but then we remove one. So in the context of ITC cuprate, this corresponds to doping an antiferromagnetic insulator. So now let's look at dynamics of this hole. We see that as it propagates, it actually reshuffles fermions, and it reshuffles them in such a way that it leaves behind a string of frustrated bonds, right? So before the hole started moving, we had spin configurations which were all antiferromagnetic between neighboring sites, but now the motion of the hole creates a string of ferromagnetic bonds, and that of course costs us energy. And therefore, early on, when people started thinking about ITC cuprates, they suggested that the right way of thinking about magnetic polarons is to think of kind of a spin-like object. Basically, you can think about it as where the hole started its motion, and the hole object, this is where the hole has moved, but they're connected by a string. And this remind us very strongly of the picture of mesons in QCD, where there are two quarks and they cannot be separated because there is a linear potential due to the gauge fields. In this case, we have like spin-in and a holon, and obviously the terminology comes from 1D. In 1D, this sort of separation into spin-in and holon is exact, and they sort of can move independently of each other. But in 2D, they are bound by the string of frustrated spin interaction, not in kind of string frustrated spin configuration. Okay, so do we see how do we see these kind of modifications of magnetic relations around the hole? So let us look at the data, this experimental data from Emmanuel Bloch's group. And what they have done was to introduce a dopant. In this case, it's a doublet rather than a hole, but there is exact symmetry between adding a doublet or adding a hole in the Fermi-Hubbard model. And what is plotted here is spin configuration, like on the left, you see spin configuration between neighboring sites, but relative to the doublet. You see that in this figure, the doublet is at the center, but it does not mean that the doublet was spin. Actually, the doublet was free to move anyway in the plane, but what we're interested in understanding is how spin configurations are modified in the vicinity of the doublet. That's why we always, in this picture, we're looking at them kind of always relative to the instantaneous position of the doublet. So you immediately recognize that this is now a 3-point correlation function, right? It depends on the relative distance between this, between the kind of spin bond that we're probing and a bond that already has two sides, so there are two spin operators, but it's already kind of conditioned on how far we are from the doublet. And what we see is that far away from the doublet, we have antiferromagnetic relations which are stronger, and then they are suppressed in the vicinity of the doublet. So, okay, well, that's somehow what we expect, right? We said that a moving doublet reshuffles the spins. And then this reshuffling becomes even more dramatic when we start looking at diagonal correlations. So now you see that far away from the doublet, we have ferromagnetic correlations between the spins, and that's what we expect in an antiferromagnetic state. And the diagonal spins should be ferromagnetically correlated, but the sign of correlations of these diagonal correlations close to the doublet is now opposite. It is antiferromagnetic. And it's very easy to understand why this is happening. Just think about, again, the motion, like we start with a hole, and then next to it, we have two fermions and neighboring sites, which have strong antiferromagnetic correlations. But now the hole moves, it displaces one of the fermions, and now we find this antiferromagnetic correlations for two fermions on the diagonal. And so when we measure spin correlations next to a hole, we have to measure this kind of original ferromagnetic correlations, right, which were there before the hole arrived, with now these correlations, which used to be nearest neighbor correlations, but they became diagonal just because the hole has moved, and nearest neighbor correlations are stronger, and that's why they dominate, and we end up having that the net, the average diagonal correlations become anti-ferromagnetic. So one can do this kind of arguments more precise. I'll not go into the detail, but more or less, let's say a zeroth order approximation, we can give the following argument. Well, the spin in principle can move because we have some kind of exchange as plus as minus terms, but like in zeroth order, let's even assume that spin doesn't move. Let's just look at the rapid motion of the holon. Well, we know that it moves as a T, like with a sort of the matrix element is given by single particle tunneling, but it moves in a kind of complicated way in a sense that it sort of leaves behind a string of flip spins. So therefore, if we want to describe what has happened to the hole, it's not enough to just say whether this holon is at any given time. We have to specify an entire trajectory because this will determine the spin configuration. And the best way of doing it is to represent these dynamics on a beta lattice, right? So every point in a beta lattice really describes an individual trajectory, like a separate path, right? So therefore, different final points of the holon, but which correspond to different paths, they will correspond to different points on this beta lattice. So effectively, we have a problem of a holon, which is like single particle problem in this case, with hopping matrix element T in the presence of linear potential, which is given by exchange J, but also a prefactor comes from actual spin correlations, which we can take either from Monte Carlo data or from the same experiments on the quantum gas microscopes. And here what I will just briefly show is that we can use this theory to compute what is the change of spin correlations next to a doublet. Because again, the picture is just as we saw before, as a doublet moves, it reshuffles the spins, and therefore a state which used to be to have these anti-ferromagnetic correlations now will have much more kind of complicated pattern, right? That say the ferromagnetic correlations decrease as we go away from the doublet. That's what you can see here, right? Again, this is kind of nearest neighbor correlation, which are anti-ferromagnetic as a function of distance to the doublet. And so this shows, like, the green line shows experiment, and only look at the green line. And this green line on the right shows this string model description. And in the bottom, we see now diagonal correlations as a function of distance to the doublet. And you see that actually they change sign close to the doublet. They are anti-ferromagnetic away from the doublet. They're ferromagnetic. Again, string model does a good job at capturing this. Okay, so we can also compare to zero temperature PMRG, but let me not talk about this. But there is actually something even more ambitious one can do, and this was done by our colleagues, Marcus Greiner's group, when they decided to look for strings, right? We said, well, as a hole moves, it leaves behind the string. So the question is, can we identify the strings in actual data? So this work was primarily done by Annabelle and Christy Chiu from Marcus's group. So, okay, just one disclaimer that at that time in Greiner's group, they could not measure simultaneously up and down fermions. They had to choose either they measure spin up fermions or they or spin down, but they could not image both of them simultaneously. However, well, on the kind of positive side, they had the lowest temperatures. But this fact that they could only measure one spin species, turns out, is not a kind of a showstopper. So the way it was done is, let's say this is an actual configuration of fermions, right? So we have two spins, like red spins, blue spins, and then let's say they choose to measure blue spins, right? So then they measure configuration like this. So then what they do is they compare this what configuration of blue fermions to the perfect checkerboard. And they look at differences between this perfect checkerboard and configuration that they detected. they see that, oh, here's a difference includes these four basically this selects blue fermions in the wrong position, and here they do not find the blue fermion where it is supposed to be. So let's call it a string of length 4. Here we see kind of a similar string of length 2, another string of length 2. Again, just like on two sides, configuration is the opposite of what we would expect. So we can then make a histogram and say that we detected one string of length 4, two strings of length 2, and one string of length 1. And then you can sort through many of the images and see like, okay, get, say, the number of strings as a function of their length. And what we should remember is that even without doping, we are looking at a quantum microscope. We are looking at a quantum Heisenberg model. It has quantum and thermal fluctuations. It's also finite temperature. So there are strings even without doping. So if you see at this kind of blue points at the bottom, this is a distribution of string length just in the Mott insulator itself, which just tells us that we're dealing with an actual quantum interferomagnet. And then this blue points on top, this is how the distribution of string has changed after the system was doped. And notice it's a log scale. So the probability of having longer string has gone up by almost an order of magnitude. And you could say, oh, maybe it's just because we now removed some of the fermions. Well, so you can see this yellow line actually shows kind of a simple model where we just take images, kind of distribution, which we had a half filling, and randomly removed some of the fermions. So that could not possibly account for the increase in the number of strings. So clearly, we get many more longer strings generated by the motion of the holes. And this green line actually shows a prediction in the increase of the distribution based on this geometrical string model of magnetic polarons. So you can see that, again, it works quite well. But then one question you can ask, okay, but what would be the smoking gun? Let's see, can we make a prediction which we think would prove that we're really dealing with this meson-like model of magnetic polarons? So let me please tell you about our suggestions, what we think can provide unambiguous evidence. Okay, so let's go back to this picture of magnons as really sort of bound states, or like more or less like a single particle problem, right? Again, let me, for simplicity, for the time being, assume that the spinon is not moving. So as we said, it's we have a tight binding model for a holon on this beta lattice in the presence of linear potential. And you can just look at the Schrödinger equation that we have to solve, and it immediately reminds you a familiar problem of electron in an electron in an electric field, right? So there is linear potential. So we get the familiar Stark ladder problem, and the analogy is that what is 1 over the mass for the fermion in the kind of Stark problem is now single hole tunneling, and then a log of the electric field is exchanged, and we know what is the energy, that characteristic of the Stark ladder. We can get it just from dimensional counting, and this immediately predicts a kind of a class of excitations in this geometrical string model, which has this characteristic scaling of T and J. Actually, this has been known for a while. So people recognized this early on when they started talking about these analogies between QCD and doped Fermi Hubbard model. But what surprisingly people did not talk about was to consider a possibility of having bound states at finite angular momentum, right? Because we know that actually in QCD, there are different mesons which consist of identical pairs of quarks, and the only difference is in the angular momentum, and they're different mesons, they have different energies. We can do the same exercise here and say, well, can we now construct states in which a holon relative to the spinon is not in a configuration with angular momentum 0, but in a state with finite angular momentum? And the answer is yes, you can construct them, and you find that just like in QCD, that the energy of those states with finite angular momentum scales is determined by the string tension. In this case, it's also string tension. A string tension, as we said, is determined by changes of magnetic exchange. So do we actually find this excitation? So this is numerical work that Annabelle and Fabian have done. They generalized the kind of simple idea. Okay, well, unfortunately, I'll skip the details. So there is a so-called single electrons, like single hole spectral function. It really tells us about what is the probability, what's the energy of corresponding excitation if we create such a magnon. And then there are these kind of usual magnons, which, as we said, correspond to bound states of spin and a hole at angular momentum 0. But then you can literally just, when you look at the spectral function, you make a configuration which the hole is created, sort of like after we make a hole, we sort of give it a twist, we give it finite angular momentum, and we compute what is the resulting spectral function. And we immediately find that the peaks of the spectral functions, are shifted, that there are new resonances. And we can look at the energy difference between the usual excitation, kind of lowest energy configuration of a single particle, and this kind of polaron type states at finite angular momentum, and their energy scales with magnetic exchange interactions. Okay, and this actually graph on the plot shows that you can like, okay, this is a vibrational excitation that we discussed previously. That's something that has been seen even in Monte Carlo. Okay, so at least numerically, we clearly see a new type of excitations of magnetic polaron. So from based on DMRG, can it be seen in experiments? So it turns out that one can make an analog of this famous ARPES experiment. So this is how one measures properties of electrons, especially in two-dimensional systems, just by launching, like in solid-state systems, by launching sending a photon which kicks out an electron, and then one measures energy and momentum of this outgoing electrons, and from this one can recover dispersion of electrons inside the solid. So one can do kind of conceptually similar, although technically it's rather different technique for fermions and optical lattices. So this is the work of Wasim Bakar's group. And you can see that while they're beginning to measure the spectral functions. So what we want to do is to basically argue that there is a generalization of this ARPES-like technique, but the idea is that before one extracts a fermion, because also in these cold atom experiments, one has to move a fermion into the third state, one has to do it not with the original Fermi-Hubbard model, but in a model in which, as we said, we're trying to give a finite angular momentum, and we can do it by modulating, say, tunneling out of phase. Let's say if we want to give angular momentum 2 to make a D-wave-like configuration, just have to modulate tunneling out of phase in the X and Y direction, and then we should see spectral features that correspond to these generalizations of magnetic polarize. Okay, so this was so far focused on a single polaron, but we can ask what do this experiment tell us about finite density of polarons? We know that in cuprates there is a transition, right? So something changes dramatically as we go from underdoped to overdoped. Again, I will not go through the details. But for people who are non-experts, the idea is that if you dope electronally, we start experiments look much more like traditional Fermi liquid theory, whereas when we talk about dopings which are closer to this antiferromagnetic mode insulator, there are very strange properties like pseudo gap. We don't have sharply defined quasi-particles. So what I'll try to argue that now we can see the same crossover in the data from the Fermi-Hubbard model. And this is based on experiments by Emmanuel Bloch's group. So I'll not go through like all the evidence. I'll just sort of show you a few facts. So what is plotted here is evolution of, this is just conventional 2-point spin correlations, right, as a function of doping, right? And here let's say, let us just, okay, so here, let's say we're looking at the diagonal. So the orange line here, right, is the diagonal correlations, and the horizontal axis is doping, right? And you see that at half filling, the diagonal correlations are ferromagnetic, but then as doping increases, actually, correlations change sign and they become anti-ferromagnetic. And anti-ferromagnetic correlations is what we would expect for the Fermi liquids, right? In that case, just by Pauli exclusion principles, we are much more likely to find fermions with the opposite spin than with the same spin next to each other. And obviously at half filling, like on the diagonal, as we said, just from the classical anti-ferromagnetic picture, we do expect to find ferromagnetic correlations. So we do see a change of sign, right, from ferromagnetic to anti-ferromagnetic correlation somewhere around 30%. Then, and that's like this kind of change of behavior is what we discussed also before, induced by the motion of a single polaron. But now let's look at a different type of correlation, but which is not nearest neighbor, but next nearest neighbor. Again, it starts at half filling being ferromagnetic, right? You see, it's ferromagnetic, but then as we dope enough, it changes sign to anti-ferromagnetic. Again, it becomes more like a Fermi liquid. We take even longer ranged spin correlation, which at half filling in the anti-ferromagnetic mode state actually corresponds to two spins which are on the same sublattice, so they have ferromagnetic correlations. Again, we see that it changes this correlation function changes sign around the same 30%. And we can convert these 2-point correlation functions computed in real space to 2-point correlation functions computed in momentum space. So at half filling, close to half filling, we see what looks like a commensurate anti-ferromagnetism, right? Something that has a peak at pi. If we dope strongly, then we see incommensurate peaks, right? That's what we would expect from some Fermi liquid picture, just by taking, you know, like response, like, I don't know, Linhart function or like RPA, just simple perturbation theory treatment of for fermions, we would get this for incommensurate peaks. And we see that the correlation function changes from this kind of more insulator-like, which is commensurate, to incommensurate, which is more Fermi liquid-like, around 30%. You can be quantitative and also about uniform spin susceptibility, right? We want to ask, well, what about things like spin gap? And what you find is that at large doping, we see spin susceptibility. Okay, maybe taking a step back. So in this case, spin susceptibility is computed again from images because it's just using fluctuation dissipation theory. One can look at fluctuations of magnetization in a subset of the system, and from this, one can then infer what is the spin response function. And what we find is that spin response function for a strongly doped system is just what we would expect for weakly interacting Fermi gas. But then the simple perturbative treatment suggests that the spin susceptibility should diverge, whereas what we see is that it saturates. Like, okay, if, based on what we know from cuprates, we would expect to see actually like even a dip, like a spin gap to appear. Probably in this experiment's temperature was not yet low enough to see like an actual kind of gap appearing in the spectrum, but clearly we see deviations behavior from a liquid like weakly interacting quasi-particles at strong doping to something which is quite different at small doping. Okay, and so the list can go on. I think I just maybe just one last thing. So like now we can, I'll just point out that if we want to describe like something even more subtle, say 3-point correlation function between a hole and two spins, what we can do, so these blue dots, these experimental data, if we do, okay, we just take a finite system and okay, obviously this, we can make it sort of look sufficiently close to experiment, but if we try to make some effective description, say if we do this geometrical string model, right? So this is, you see this gray line, sorry, you can hardly see it. It works quite well for small doping. So that's in the regime of when it's mostly individual polaron physics, but it fails at larger doping. On the other hand, if we take this model like free fermions or like slightly decorated RVB type models, they work quite well at large doping, but they fail for small doping. So I think we clearly see this kind of distinction that this geometrical string model and this individual polaron physics works until a certain doping of around 30%. And then at larger filling, we get much better description using mean field models, such as, let's say, RVB type model. Okay, but of course, the key question that we want to see is magnetically induced pairing, right? That, of course, is what drives interest in the strongly correlated system. So today I'll show you kind of preliminary results of the first evidence of actually seeing pairing in the kind of Fermi-Hubbard type model. It's not the plain vanilla Fermi-Hubbard, but it's kind of in the same family of models. So the idea actually came again from Annabelle and Fabian. And first, we discussed it in the context of bilayer systems, but then it was actually done on experimentally on a ladder. So let me just talk about a ladder system. So consider a ladder, right? Okay, most of us have played with this. So we have hopping of electrons in individual chains, hopping between the chains, we have exchange interactions. And then the idea that sort of actually Fabian started working on some time ago was, well, what if we modify these systems by using the trick of mixed dimension? We can apply kind of a potential energy bias between the two chains in such a way that single particle tunneling will be suppressed. Right, that there is like such imbalance between tunneling that single particle can no longer resonantly tunnel, let's say, from one chain to the other. And naively, like in solid state systems, we would say, oh, if no, well, it used to, if there is no single particle tunneling, there is no super exchange. But in fact, here, it's the other way around, because if now the fermions moves to like from the higher energy side goes to the low energy side, actually intermediate state no longer has energy of U, it has energy U minus delta, where delta is this bias. So actually virtual state is now low in energy, and therefore we're enhancing exchange interaction. So by applying this kind of bias between the two chains, we achieve two things. We suppress single particle tunneling, and we enhance exchange, interlayer exchange, or in this case, sort of between the two chains. Why is it good? Well, okay, let's just think about the effect of this on pairing, right? What we hope to see is, okay, kind of our cartoon picture of ladders is that we have strong singlet correlations on individual rung, and then when we have two holes, they'll stick to the same rung so as to disrupt, as to have the least disruptive effect on these singlets. But in reality, this actually competes with the phenomenon, this sort of having two holes on the same rung competes with their kinetic energy, because this way they cannot delocalize, right? They sort of stand in each other's way. There is nothing there to move. And that's why actually single particle tunneling favors having two holes on different rungs. Therefore, when we suppress TPROC, we actually make it better for holes to be on the same rung. At the same time, by making GPROC stronger, we're really forcing kind of a much stronger singlets on the rungs, which again enhances this tendency for two holes to stick together. And therefore, actually, both of the major effects of this kind of tilted lattice work in the direction of enhancing pairing. Another way of thinking about this phenomenon is to say, well, let's consider like starting with two holes on the same rung, and then, you know, we have fermions or neighboring rungs forming singlet configuration. But now if one of the hole moves, then the singlet configurations are no longer on the same rung. They are kind of on the diagonal, and therefore the system no longer benefits from strong exchange interaction between the chains. Okay, so let's see whether this works in experiments. Well, this is an image, and so here you can see positions of fermions in the two chains. This is from experiments done by Sarah, Timon, collaborators in the Emmanuel Bloch's group. And what you see is that two holes, right, are clearly sitting on the same rung. Okay, well, you can say it's a specifically selected image, or we can just measure correlation function. of two holes in the between the two chains. Like, so if there is a bias, this is a red point, and you can see that there's very strong enhancement of probability when the relative distance is 0, meaning when two holes are really on top of each other. And this effect completely disappears. In fact, it's the opposite when we go back to the kind of original ladder, right? When there is no bias, then we're actually very unlikely to have two holes on the same run. So again, we can discuss, like, because probably we believe that there is pairing at low enough temperatures, and maybe this just shows that we should be kind of, well, first of all, we should get lower temperatures, and secondly, that pairs are probably more delocalized when there is no bias. So just by adding a bias, we just make this pairing much more obvious. It really is now pairing of holes on the same run. And then our colleagues also started measuring interaction, basically kind of self-organization of the Cooper pairs, and you can more or less see that they behave as bosonic particles with fairly strong repulsion. So when there are two pairs, they try to stay away from each other as far as possible. So you could say, oh, maybe it's a stripe, and then there is a preferred distance between them. But no, let's say when they look at three whole pairs, they see that again they just try to make an equidistant position. So this is more or less what you would expect if you had bosons with non-local repulsive interaction. Okay, but so then let me at least say a few words about using tools of machine learning, right? We said our output is images, so can we use the powerful technique of data science and machine learning to analyze these images? And that, again, is work led by Annabelle and Christy, and then we also later collaborated with a group of Una Kim at Cornell. So actually what the analysis that was done sort of involves two theoretical models. So one model we already discussed, this was the geometrical string model. The other model is a pi-flux RVB. Again, experts know what it is. For non-experts, I'll not go into detail. That would you say it's some kind of mean field theory, right? Remember, like in this geometrical string model, what we emphasized was that spin configuration is strongly affected around individual hole, right, or individual doubling. So by contrast, in this kind of pi-flux RVB, the assumption is that when we dope holes, this is bad for magnetism, but so magnetism gets suppressed everywhere uniformly, right? It assumes that like if motion of holes on the S just suppresses magnetism essentially the same way in the entire system. And so then the question is, okay, if we know now that convolutional neural networks are very good in looking at images and separating cats and dogs, so can we use them to do something useful for humankind and to separate different theories of strongly related electron systems? So this is what Annabelle has done, and she actually implemented two types of analysis. So in one, the data was trained, convolutional neural network was trained on three types of data. So we have two theories and we have experiments. And then, okay, there was a training set, and then there would be a new set. And so she would look at how well this convolutional neural network can discriminate between these three classes. And what you can see that actually the pi-flux model was usually kind of much more easily discriminated. Like it clearly, okay, if the data was strings, so experiment, then okay, it had fairly small probability of assigning pi-flux. And again, these numbers, you can be surprised, oh, why is it not zero? So this is all assignment of probability based on a single image, but a single image is fairly small, it's like 8 by 8. So there's limited amount of data. So even like this small difference, actually, if we use several images, then it immediately sort of translates into much larger preference, and I'll show you later on. So, but the bottom line is that this neural network could easily distinguish pi-flux from experiments or from this geometrical string model, but it had a hard time distinguishing geometrical string images from experimental images. So which suggests that geometrical string model works better, at least like, and this, so this was analysis done at fairly small doping. So another approach, another study done by Annabelle was to train the data just on two theoretical models, like either geometrical string or the pi flux data. Okay, and then the network was trained, and then Annabelle would bring experimental images and ask the CNN to assign it to one of the two theories. And again, you should keep in mind that this is based on a single image, which has limited information. And for small doping, with a fairly large difference, experimental images were assigned to the geometrical string rather than the pi flux RVB. And then for larger doping, and some were actually above 15%. And that's actually roughly the doping level, like I would say, like 20% is where if you do an estimate of the size of magnetic polarons, you know, that's kind of distance between a spin and a hole, and if you start packing them, that's where they begin to overlap. So that's kind of the doping range where we no longer basically kind of both geometrical string and pi flux RVB seem to do kind of similar from the point of view of this neural network. Of course, one thing that kind of does not look satisfying to kind of physicists is that this looks like a black box. Okay, well, a neural network prefers this theory and not the other one, but how do we know? Like maybe it's some I don't know, maybe some something, I know, some imperfection in images. Like, can we understand what is the physical information that we extract from it? So actually, so Cole, Miles, and Unakin, they developed a special sort of architecture of convolutional neural network that was designed to extract information, not only to discriminate between different classes, but also to tell us what were the correlations based on which the neural network was making its decisions. And as we look at them, so this actually shows you the results, or I sort of have to skip over all of the details, but you can, so this really shows you the patterns, which turned out to be crucial in this sort of convolutional neural networks making a decision. And they pretty much look like what you would expect. Remember when we said of a change of spin correlation induced by a hole, remember we said, oh, when the hole moves, now it displaces the spin. So now you can see that we have spins on the neighboring sides, which are ferromagnetically coordinated, right? And that is just a result of the hole motion. Or we have spins on the diagonal, right, which are now anti-ferromagnetically correlated. And this is a result of the hole motion. So it's really this kind of, okay, so the fact when this sort of square is dark, that means it did not have a very large weight. It's mostly like in 3 and 4 spin correlation functions that were sort of playing. Yeah, this is a 3-side correlation function. See, it's like it's a whole spin up and spin down, right, on the diagonal. So this was sort of the most important feature that the neural network was picking up to identify a geometrical string model. Okay, so this is, of course, quite exciting progress of quantum simulators, but I think one of the questions is, can we use them for something outside of, narrow interest of physicists? And this is, so at least one of the direction that we're excited about is to try and use quantum simulators and quantum technology in general in the context of NMR inference. So in a way of introduction, let me just point out to you that we live in the era of kind of fairly imperfect quantum computers. So this is what John Preskill coined as a noisy intermediate scale quantum technology, or NISQ technology. So we have a kind of number of qubits, which is, okay, I guess now they're reporting a kind of scale of 200s. But they all still suffer from kind of decoherence, right, and imperfection of the gates. So our goal is to, and the question is, can we find problems for which this kind of NISQ technology can already provide useful solutions. And John Praskill also suggested that for this, we should not look for classical optimization problems, because there is no real we don't really have mathematical proof that that there will be very strong speed up due to sort of quantum computers, but it's much more likely that quantum computers will be very helpful for solving problems which are intrinsically quantum, right? So sort of in the spirit of this Feynman simulation, quantum simulation idea. And this is the problem that actually our colleagues from medical school pointed out to us. They said that, well, there is a big outstanding problem with biomedical sciences, and this is from the spectrum of NMR to reconstruct the chemical. Okay, I'll sort of skip all the details, but formulate it to the kind of physics problem. Let's at least figure out kind of intermediate scale problem. We have a spectrum computed at infinite temperature, and this is just because NMR, like in biomedical research, has to be done at room temperature, and room temperature is orders of magnitude higher than typical energy scale of these magnetic interactions. So we know the spectrum, and we want to figure out what is the Hamiltonian that gives rise to the spectrum. And here I show you the example of the simplest type of problem. So we are looking at NMR in liquid, so kind of dipole interactions average out, and we're also looking at kind of large magnetic field. Later on, we'll talk about this is kind of the simplest regime, but classical NMR, classical tools for doing inference from NMR probably works best, but that, okay, it's just for illustrative purposes. So again, I'm not going to talk about, like, obviously you can say even after you know the Hamiltonian, okay, you still have to determine what is the actual molecule, but you know that knowledge of the Hamiltonian has a lot of information about like chemical structure, about symmetries and so on. So it is very useful for identification. Okay, since time is short, I will not give you all the details, but at least I want to emphasize the key idea. So how does this NMR inference work? So what you have to do is usually you make a guess about the Hamiltonian and you compute the spectrum, you compare it to an experiment. Now, obviously there is some disagreement, so you adjust your kind of assumption about the Hamiltonian, you compute the spectrum again. And because we're dealing with infinite temperature, then in principle, we really have to solve, to compute the spectrum, we have to deal with all the states, and there is exponential number of the state. Therefore, like if we really wanted to do it through exact diagonalization, this would require solving exponentially hard problem over and over again. So it turns out that on a quantum computer, even if we have this, all-to-all interaction, the complexity of just computing the spectrum does not scale exponentially with a number of spins, it only scales quadratically. So just computing the spectrum, therefore, is much more efficient because we're simulating kind of quantum dynamics on a quantum hardware. So therefore, the idea of, and that was really kind of is the work of Dries Sells, is to use a hybrid procedure where the spectrum is computed on a quantum computer, but then the inference kind of improvement in our kind of assumptions about the Hamiltonian are done in a classical machine. And then there are other kind of interesting questions you can ask. Okay, so how do you update? It turns out that sort of like simple gradients do not work so well because the landscape is very rough. Basically, okay, you're trying to fit a spectrum which has many peaks, but if you sort of fit one of the peaks, then your more or less your system is already stuck there. So Dries had to kind of really use his tremendous knowledge of data science. For example, he looked at biological molecules. Let's do it again. It's just for the purposes of demonstration, which is have 4 spins. And then he found that if one does very simple just clustering of the spectra, one finds that all the spectra of biologically relevant molecules, they separate into 4 separate clusters. And in fact, if you look at them, you see that there is a chemical structure difference. Let's say like this group, so that would be cluster 1, right? It usually it's a structure which basically you see kind of have multiple degenerates. And this multiple degenerates comes from the fact that there is a methyl group. There are 3 identical hydrogens, right? And that's why kind of many peaks coincide. Or on the other hand, if we look at the spectrum, so this is cluster 4, right, where we sort of have the least amount of degeneracy, that's what, and this all corresponds to molecules which have this sort of benzene ring type structure that is, to physicists, would look closest to a spin chain. So that's what, as we said, that there is kind of information about chemical composition in the NMR spectrum. But now what is also found is that if you start with a random spin Hamiltonian, if you try to get to the correct Hamiltonian by sort of improving, doing this inference protocol, you get stuck, you do not succeed. But if you start in the vicinity of the correct cluster, then you're close enough, then you can converge. And that can be done using a kind of certain variational bias algorithm that he developed, which works more efficiently than the usual gradient descent. But of course, the key question is, can you do something with actual current hardware? So this is where we're fortunate to collaborate with the Maryland group. And what was done, it's a simple example of just 4 spins. However, yeah, like here you can see this group. However, this is zero field NMR. That's actually the regime in which classical NMR inference also has a hard time, because like in large field, all the eigenstates would be separated based on a Z, but there is much more kind of complexity in zero field data. And what you are seeing here is a comparison of the actual NMR measured spectrum and computed on the ion-based quantum computer. And to make it happen, they had like a large number of just engineering problems had to be solved. So our experimental friends told us, look, there is a finite budget of gates. Like we cannot do more than like 100 to 200 gates, like for iterations. So, you know, like you cannot do your favorite naive tractorization algorithm, which would require many more hundreds of gates. Because I remind you, what's challenging is on a quantum computer, you can apply discrete gates, but we're trying to implement a Hamiltonian, right? And actually, it's not, we're not choosing a Hamiltonian that is fine-tuned for our machine. We have to really implement a Hamiltonian that's peculiar to this molecule, right? Once we've chosen a molecule, we really have to implement this specific Heisenberg Hamiltonian. And then another challenge was, well, if you look at the width of this peak, it's very narrow. So if you naively try to estimate how many time measurements you would have to do in order to be able to resolve peaks of this width, you would come up with a number of 4,000. And our friends told us, look, even sort of doing 100 measurements is going to take a few days of the work of the group. So again, find a way to compress the entire procedure into measurements done on just 100 time steps. And that's something that again, Kushal and Dries figured out that could be done using compressed sensing technique. So anyway, that you can see that the agreement is kind of quite good, except, okay, there's interesting fact. So here you can see that, so these hydrogens, right, they form a very degenerate structure, which is sort of connected by symmetry. And because of this, certain matrix elements vanish. And so like in actual NMR data, there is no peak like a J/2, even though there are states. But when you do quantum simulation, you do pick up this peak because even though you implement a symmetric Hamiltonian, but your noise, like actual hardware noise, does not respect the symmetry. So that is, okay, something that I guess you can say maybe it was just an unfortunate choice of the kind of model to implement. But other than that, okay, you can see the agreement is quite remarkable. Okay, and then you can ask, well, okay, that's a demonstration for spin, who cares? But what's the future? Like, can we get to something that's really interesting? And for this, we talked to our colleagues who do actually like kind of classical computations of inference. So for them, we asked them which molecules are hard, as they have basically some molecules which have many interacting spins, like some kind of clusters. And we took an example of, let's say, several of the molecules, which they say are already computationally challenging for them. And then we can ask, so what are the resources needed in order to be able to compute these kind of challenging molecules. And again, so this, it turns out, is also an interesting optimization problem. I already told you that we're trying to simulate evolution, but we do it with a discrete number of gates using tractorization. And then it's really an art of compromise, because if you want to minimize tractorization error, you want to have a tiny time steps, but which means many gates, but there is finite fidelity, there is hardware error, and for this you want to have smaller number of gates. So that's why you really have to, given the fidelity, you can choose what's the optimal number of gates. And fortunately, what is special about this NMR inference, which say makes it different from factorization, we do not have to do our computations perfectly. We only have to, because nature itself, like NMR spectra, are sort of have the intrinsic decoherence, and therefore we just have to make computations as well as nature does them, and that actually allows to sort of find this optimal balance. Anyway, since my time is basically up, so what we find is that in order to be able to compute these kind of computationally hard molecules, to do compute the NMR spectra, we need infidelity of the order of 10 to -4, and we need to be able to have the number of circuits of the order of 10,000, 100,000. So again, the hardware is not there yet, but our experimental friends sort of are hopeful for this in the next 2 years. And actually, this number of 10 to -4 is often used in the context of error correction. But again, I want to emphasize a key difference. So people often say, oh, when the infidelity gets so small, we will be able to do error correction. What I say, no, if it gets so small, you're in business already. You do not need error correction. And the reason for this is because you do not need to get a perfect answer. You only need to get an answer with the same accuracy as the data that you are taking from experimental NMR. So because of this, I think this NMR inference is an actually promising direction of applying quantum computers and quantum simulations. Okay, with this, let me conclude. I try to give you kind of an overview of some of the work that has been done in the context of quantum simulators, mostly in simulations of the Fermi-Hubbard model and using cold atoms in optical lattices, and then also more recently using simulations of spin models based on ion sort of crystals of ions quantum computers. Thank you.
Okay, thank you very much, Eugene, for a very inspiring talk. I guess we have time for questions. So please raise your hand virtually so I can. Okay, let me, while people, okay. Xin Lei Wu, you. Could you unmute yourself, please?
Okay. I'm wondering if we could go back to the page describing how we identify the geometric string.
Yes. Sorry, for some reason I
got stuck.
I'm stuck here. Oh no, okay, it started moving. Right, yes.
Yeah, I'm just wondering, as you mentioned that the energy of this kind of string is proportional to the length of the string. So I'm wondering if we could identify the J corresponding to the string by the population of different of strings with different lengths.
Well, in a sense, we solved the opposite problem because the string tension is determined not only by J, but also the strength of nearest neighbor correlations, next nearest neighbor correlations, right? Because what happened, you start with spins which are nearest neighbors and you make them next nearest neighbors. So the line, this kind of green line, was based on taking spin correlations from the experiments. Actually, I forgot whether the experiments at Half-Filling or Monte Carlo. I think actually experimental data. And based on that you compute a string tension, and that's how you get the distribution of the string length. That's like this green line. But of course, you can then do the inverse and you say, oh, let me now change, let's say, some knowledge, but it's not just J. Again, we would have to because what enters into the string tension is really knowledge about spin correlators. So it's more than J. But in this case, like what J is known. That's the advantage of cold atom systems, because all microscopic parameters are known.
Okay, maybe another question. Is there a possible way to identify the correlations between the holes, or let's say in this case, between the doublets?
Sure, right. That's actually, yeah. I mean, that's exactly how, like this whole correlation, right? That's exactly, that's what you wanted, right? So this is correlation between the holes, and actually, okay. So in fact, I guess you're asking, like, what about true, like real two-dimensional Fermi-Hubbard model? Did they look at this correlator?
Yes.
And the answer is yes, they did. So what is your guess? Do they find bunching or not? Do they find kind of an enhanced probability to have holes close to each other?
Yeah, okay.
Well, the answer is no. Actually, they find that they are less likely to find holes close to each other. So it's more like, looks like repulsion. Again, I don't think it kills the idea of having bound states. Like, let me bring up an argument from Feshbach resonances in cold atoms. You know that if you have a very shallow bound state, you know that your system is characterized by large positive scattering length, which looks like repulsion. So if mostly what we see in a scattering states, then what the scattering states will experience is effective repulsive interaction, because there is a bound state. To start seeing bunching, temperatures has to be low enough that we really start occupying those bound states. So of course, it's like a speculation. Okay, if you want experimental facts, for now, in the two-dimensional Fermi-Hubbard model, at temperatures which are currently available, they see something which looks like kind of holes are trying to stay away from each other.
Okay, thank you.
Okay, I have a question. So basically, while it's commonly believed that somehow high temperature superconductivity is somewhat described by the Hubbard model, there's still some doubt that maybe there are additional terms. And I guess in the cold atom experiments, I think we have fairly good control, and we can say that this is more or less definitely a Fermi-Hubbard model. So maybe you can somehow try to understand what is missing, or there's nothing missing in the modeling of the material properties. That you see like key differences between the two experiments.
Hopefully this will be then kind of the next step, right? If we really roll out pairing in the plain vanilla Fermi-Hubbard model, then we can start adding analogs of electron-phonon interactions by adding some bosonic mixtures.
I see. Okay, that sounds exciting. I see that Asa has a question.
Hi, Eugene.
Hi, Asa. One time.
Question about the last part. Searching for the Hamiltonian that will give you the difference spectrum. You kind of have to eliminate all unitaries on that Hamiltonian, right? That would not change the spectrum. So,
yes,
so,
sure.
so
right.
how
all
do
the
you,
symmetries.
So not just symmetry, but any kind of unitary that, give you a different Hamiltonian. I don't know. Okay, you can call it symmetry, but right, when you look at the spectrum and you want to reconstruct the actual operator, the spectrum is invariant on any unitary operation. So do you choose special Hamiltonians that all unitary operations will give you something non-local, or would mix kind of spins far away from each other? Is that a consideration in your choice?
Consideration is that let's say generally we're only allowing two-body interactions. So like if you make some complicated interaction, then many-body interaction, then yes, I agree. Usually if you do this unitary transformation, I would say you start generating kind of multi-spin interactions. So these ones we do not include.
The second thing you have to worry about is whether the Hamiltonian commutes with your particular operator that the light couples to, right? Or some parts of the Hamiltonian might commute with it, so you won't be able.
But in this case, like in NMR, right, it's really just magnetization. So it's total magnetization.
Total. Okay.
So it's yeah, I guess you can say again if it's liquid type NMR, you know that interactions are CO2 symmetric. Once we talk about, say, NMR on solids, and there are dipolar interactions, even interactions do not commute. So in most cases, we kind of understand, because maybe I should say that, that there is also some kind of background knowledge, like say in this liquid NMR, let's say, that dipolar interactions should average to zeros. If it's dipole, again, it's more complicated. But I don't see like but maybe what's not obvious is, so what breaks us to symmetry, right, is the fact that Zeeman field is different for different spins, right? So again, in an NMR language, that's okay. So did I write it? Yeah, you see, this is what they call chemical shifts. Right? So this is the thing, because basically you can think about it that every speed, like every proton, like say in this case that we looked at, is in different, it experiences different the magnetic kind of screening of the magnetic field. Okay. So that's why because otherwise, if everything was SU2 symmetric, then your entire NMR spectrum would be just one peak.
Right. Okay, thank you.
Okay, so we are kind of running out of time, so we might have just time for one more question from Erez.
Actually, two short questions. One about this part. So what you're trying to do here is to identify the molecule through the Hamiltonian, or
ultimately
find the Hamiltonian.
Like as physicists, we're only trying to find the Hamiltonian.
Yeah, right.
Okay, that would be the next step. Would be a kind of like probably more classical machine learning. But again, my argument is that Hamiltonian knows a lot about symmetries. Therefore, it has much more it contains information which is much easier to digest than just like the nature of the spectrum.
I see. And about the first part, so what was the U over T in the experiments that you showed?
I think it's about 8, and I try to stick kind of to the regime close to cuprates.
So this in the small doping regime, where kind of the string picture is more applicable. Is there a way to estimate what's so there's sort of a bound state between a holon and a spinon? So is there a way to estimate what's the effective mass of this bound state?
Yeah, you can compute the dispersion, but so far, like say from what we get, because that's something people have done previously using various, even some Monte Carlo approaches. What this geometrical string gives you seems consistent with this earlier work.
Right. Yeah, thanks.
I mean, it puts the same kind of physics that you can say, look, it's okay, that's something that I did not have time to talk about, maybe what you're leading to. Can we study dynamics? So there was actually an experiment by Marcus Greiner. Sorry, I cut it out because of limited time. So instead of looking at the spectral function, what they do, they start with a hole that was localized, and then they let it go. And then they see how it spreads out. And what you can see is that at short time, it spreads out on the scale of T, but at long times, it spreads out on the scale of J. And that's exactly what we expect. At long times, low energies, we have real quasi-particles, and for them, the dispersion is set by J. Yeah. And so at least in that case, right, what we could compare to experimental data is this real-time dynamics, right? How does the expansion occurs because at short time, right, okay, more or less I can say the polaron is being formed, right? We let the column start moving around the spin, and then later time is when the polaron has been formed, then it starts, you know, doing diffusion kind of. So yeah, and that seems to be, so if we like it's really kind of Fabian and Annabelle, they have both like computed the effective mass, you know, compared to Monte Carlo, but they also checked against this real-time dynamics of the whole expansion.
Thanks.
Okay, so I think now is a good time to thank the speaker one more time for a very interesting talk.
Thank you for the invitation, and if people have more questions,
yes,
shoot me an email.
I just want to,
happy to continue the discussion.
Sure, yeah. So you can just speak up if you want to ask questions. Okay. So maybe I have a question. So it seems like the main limiting factor is, again, is temperature in those experiments. So you really the relatively high temperature phase over there, or?
I say yes. Also, system size you can worry about, but they actually making tremendous progress. I think for bosons, like in this quantum gas microscopes in Munich, they now have much larger system sizes, and they're working on doing the same things for fermions. But probably, yeah, the big challenge, like in order to really take temperatures down to the regime, we would like to study properties of the Fermi-Hubbard model as relevant to cuprates is temperature.
I see. And let's say for, okay, given that there is a dome there or something like that, so how much you should improve temperature-wise to see superconductivity, or it's not clear?
Again, okay, it's just was discussed previously. We don't know whether superconductivity is there or not, but roughly you can say, like again, based on cuprates, maybe it's 1/10, like TC is 1/10 of TNAL, and maybe you see these guys are making progress. I would say currently temperature is maybe like half of TNAL, so there's still like a factor of, I don't know,
I see. Okay.
5, maybe 3.
And it now boils down to tweaking, you know, the current machinery, or is that you need like a really novel breakthrough to bring this down furthermore? Like it's like you need some few incremental, you know, progress, or is it really a new kind of a system that would allow you to reach there? Or it's not clear, I don't know.
Oh, it's obviously not clear to me. I think different people are trying different things. So some people, I've heard arguments that, yeah, that there is some fundamental issue. You have to design kind of really dramatically improve your vacuum.
I see.
Some people say, no, you like, again, like say Greiner's group managed to dramatically lower the temperature by designing kind of the trapping potential in different ways so that there was some kind of metallic kind of reservoirs at the edges, and that was sufficient. So I think these guys are creative, so I'm sure they'll try different things.
Okay.
What happened in this case for the coefficient transport, like the shear viscosity, susceptibility in this case, for the Fermi liquid?
So susceptibility is this, right? This is spin susceptibility. And like if you compare it to Fermi liquid, so these are like, okay, it's if you do some kind of somewhat improved RPA, so this would be, well, okay, no, sorry, this is, I think this is bare RPA, this is somewhat like a solid line is an improved RPA. So you see that that large doping, like spin susceptibility agrees with what you get from Fermi liquid, like RPA type expression, but it clearly breaks down close enough to half filling. So transport measurements are not the most natural measurements for the setup, although there are groups like Tillman-Esslinger which actually do transport experiments. But the closest, I would say, was this experiment of like releasing a hole and then measuring how it expands, but it kind of is a slightly different way of thinking about transport. So it's more like non-equilibrium transport. So you can extract some analog of a diffusion, well, not diffusion, more like an effective mass of the particle, like at long times, or like diffusion coefficient.
Okay.
Hey, can I ask a follow-up question?
Sure.
Yeah, can you still go back to the slide that has 2 layers of yeah, 2 layers.
Sorry, 2 layers.
With holes.
Yeah, this one.
Yes, this one. Yeah. As you said, like if there are like one hole in one layer, another hole in another layer, experimental result like confirming can form a pair. So and there is like no evidence for like two holes in one layer that can form a pair. So there is some possibility that it can be impulsive interaction, as you said. So I wonder whether like if there's one hole on one layer and 2 holes on the other layer, can these 3 holes also form a pair? Like a bound state, something.
Okay, so your question is other situation where we
involving multiple holes, like forming a.
Okay, well, I'm glad you asked. So first of all, like if we start binding Cooper pairs to each other, that's how we get stripes. So, like, you know, one of the questions that was interesting to check already in this data, whether we will see that somehow, let's say, this whole pairs clustering, which could be phase separation of, I don't know, forming some larger structures. But if you want something in which, like maybe 3 holes, that's of course much more exotic. So we have a different theoretical paper where we argue that this should happen on a triangular lattice, like in the regime of large spin polarization. But I don't think, I'm not aware of suggestions about, let's say, forming this sort of triple hole bound states on a square lattice or on a bilayer square lattice. I mean, in other lattice geometries, such predictions have been made.
Okay. Nice. Thank you.
And again, in principle, there are several groups which have triangular lattices. For example, Klaus Engstock's group in Hamburg is working with fermions on a triangular lattice.
Okay. These are no further questions. So we really hope to see you now more frequently in Israel, now that you have reduced your flight time significantly. And hopefully your next talk will be in person. So thanks a lot.
Oh, thank you, Snir, again for organizing this. And I'll be
of course.
happy to hope it's now a short fly away.
Okay.
Thank you,
Thanks
guys.
a lot.
Bye.
See you
Thanks.
soon.
Bye.
Hey, thanks a lot. Have a nice day for you guys.
Thanks, everyone. Bye.